Okay, so here's the solution for the physics for the physics test. So the initial rotational speed, angular velocity, was 200 RPM. So you multiply by 2 pi, divide by 60 to get 20.9 radians per second. And so we have the initial angular velocity, the change in angular position, and we know that the final angular velocity is 0. So I use this equation to solve for t. So if you solve for t, you'll get 2 delta theta over omega plus omega 0. You plug those in, you get 33 seconds. And then with that time, I can use the second equation to find alpha. So I can solve this equation for alpha. And I get negative 0.63 radians per second squared. Okay, so the second problem is a satellite problem. So the first thing you have to do is calculate the orbital radius. So that's the orbital height plus the radius of the planet, or in this case, the moon. So you get the orbital radius is 3.74 times 10 to the sixth. This equation, which was the result of setting equal to centripetal force equal to gravitational force, and eliminating common terms. So you use the universal gravitational constant, the mass of the moon, and the radius, orbital radius. And if you solve for v, you get 1140 meters per second. Now the velocity as it travels in the circular orbit is the distance traveled divided by the time, or the distance traveled, where the distance traveled is the circumference, 2 pi r, and this is the orbital radius. So if you plug that into here, you get, and solve for t, you get the period, time it takes to go around the moon once is 2 pi r over v. And you come up with 20,600 seconds, and if you divide by 3,600 seconds per hour, you get, it should be hours, 5.72 hours. And then to find the gravitational force, just use the law of universal gravitation. So it's universal gravitational constant, the mass of the satellite, the mass of the moon, and the radius, or orbital radius. The next problem is you have these two astronauts orbiting around the center. So the center of rotation is halfway between. So when we calculate the moment of inertia, we use 25 and 15, not 15 and 30, even though you do get the same answer if you use those incorrect radii. You convert revolutions per minute to radians per second by multiplying by 2 pi and dividing by 60. The initial moment of inertia, that's a 25 meter radius, is this number. At the 15 meter radius, you get this number. They're large because, there's people are heavy and the distances are big. So conservation of angular momentum says that the initial angular momentum is equal to the final angular momentum. If you solve for the final angular velocity, you get it to be 0.306 radians per second. Okay, number 4. So you've got this beam that has two masses plus the mass of the beam with these dimensions. And so here's my free body diagram. I've got the two support forces on the left. So I've got the cable tension on the right. And I break the cable tension up into an Y component and an X component. You've got the weight for the 15 kilogram block, the weight for the 30 kilogram block, the weight for the beam, which is located, we concentrate that in the middle of the beam. And the middle of the beam would be half of 12, which is 6. So you've got distances 3, 6, 9, and 12 meters to the four forces. Since we're summing the forces around the support, we don't have to worry about those when we calculate torque. Okay, so if we sum the torques around the left support, we'll have the first mass, the first weight at 3 meters, the second the weight of the beam at 6 meters, the second weight at 9 meters, and the Y support force at 12 meters. And these three are negative because those would cause a clockwise rotation, which would give you negative torque, whereas the T sub Y is pulling upward, so that would give you a positive torque. If you solve for T sub Y from this equation, you get 478 newtons. Then you can use geometry over here for the cable to relate T sub X and T sub Y, because the ratio of those two has to be 7, associated with an angle of 70 degrees. So if you solve for T sub X, it's Ty divided by tangent of 70. So we take that 478 divided by the tangent of 70 gives us 174. Now to find the support forces over here, we sum the forces in the x direction. There's only two forces in the x direction. The support force, which I'm assuming has to be going to the left, and T sub X, which is going to the right. We know that because of the direction of the cable. So if you solve for R sub X, it's equal to T sub X. So it's 174 from the previous step. And I guess, because it's positive, I guess the right direction. Then you can sum the forces in the y direction. So you've got the two masses and the weight of the beam going down. You've got T sub Y going up from the cable, and you've got R sub Y either going up or down. I assumed it's going up. And if you solve for R sub Y from this equation, then solve for R sub Y from that equation, you get 404 newtons. These are the two left support forces. And then to find the total tension in the cable, you'd use Pythagorean theorem from this force triangle, and you get 509 newtons. Okay, and then the final one, you got the torque being applied through the pulley, and then you've got the disc that's larger, just like in the lab. So to find the moment of inertia of the disc, you use the radius of the disc. And that's the only place, and I mentioned that a couple of times during the test, is the only place you use radius of the disc is for the moment of inertia. To relate the angular speed of the disc and the pulley to the linear speed of the hanging mass, you use this relationship where you use the radius of the pulley because the mass is attached to this whole thing, this rotating thing, by the pulley, which is 0.36 meters. So you get alpha is negative 0.28. And it's negative because clockwise here, which is negative, means down, which is negative. So they have the same sign. So here the block is negative 4.6 meters per second. Therefore, alpha is negative 12.8. Now to find the tension, we just sum the torques on the disc. And the only torque we have is the one caused by the string pulling this thing down. There's going to be a weight of the disc and the support for the disc, but those go right through the center, so they don't create a torque. It's negative because it's going to rotate clockwise, and as a consequence, T is positive. So you get 86.4 newtons, using again the radius of the pulley, because that's where the string is attached. And then you can look at the hanging mass. So we have the tension of the string pulling up, we have the weight pulling down, and they're not going to be equal because it's falling. The difference between the two is the mass times the acceleration. So we know the tension, we got in that previous step. We don't know the mass, but you can see I can move these two terms to the left-hand side because the weight is the mass times the acceleration due to gravity. So this becomes positive. Factor out the mass, divide by the sum of these two other things, and you plug your numbers in, and you get 16.6 kilograms. And that is all there is to it.